Good morning. So today I actually want to start with a rather unique question. And that question is, what defines Canada? Or more generally, what defines any northern country? I am an American who has resided in Canada for many years, and I've had to pick up on some unique aspects of Canadian culture. Sport, government, food, art, or is it the landscape that defines Canada? What I've come to learn is that Canadians have a deep-rooted love and a strong passion for the North as a source of inspiration, of adventure, of wilderness. And despite the fact that most of the Canadian population lives within just a few hundred kilometers of the US border, I think most Canadians have a very profound understanding that the North is built upon and really depends on frozen ground. Permafrost underlies more than half of this country, so I define Canada as a permafrost nation. But what happens in the North will not stay in the North. And so permafrost in Canada has the potential to influence global processes. Now, there's a number of processes in the North that can affect the global scale through things like climate feedbacks, and permafrost carbon is just one example. There is almost twice as much carbon residing in permafrost soils as is stored in the entire atmosphere. In its frozen state, currently, this permafrost carbon is protected from decomposition. But the concern is with warming and increased thawing, this carbon could be increasingly vulnerable to increased microbial activity. Now, unlike vegetation and animal growth, we tend to think of microbial activity as being limited by carbon as energy. And this microbial activity can release permafrost carbon in the form of either CO2, carbon dioxide, or as methane, where these gases can contribute to the greenhouse gas effect in the atmosphere. So we are interested in scaling these kinds of effects from the plot scale to the global scale. But to do that kind of scaling, we need models. The models that are currently simulating permafrost carbon release really are focusing on active layer thickening, the gradual processes that affect permafrost from the top down that expose centimeters of soil very incrementally over time, but on a widespread basis. Models are not currently accounting for a number of lateral processes, thermokarst and thermal erosion. These kind of processes can cause a real diversity of surface expressions, but they all share a few common traits. All of these processes can occur extremely abruptly, unlike very slow and incremental top-down thaw. They also tend to affect the entire soil column, again, under very short conditions sometimes, very rapid conditions. As part of the permafrost carbon network, we set out a number of years ago to answer a very simple but tough question. And our research question is this: what are the potential carbon releases that we can associate with thermokarst? And how do these thermokarst-related carbon releases compare to estimates of permafrost carbon release associated with top-down thaw? And I use the term "we" here in the royal sense. Many of the collaborators of the work I'm going to talk about are actually in this room today. It's a very good group of strong collaborators. Now, to address this issue, the first step we needed to take was to get a better understanding of some of the spatial trends in past thermokarst environments and how we expect thermokarst to continue to proceed on the landscape. We created a decision tree, a probability-based spatial framework for trying to understand land vulnerable or predisposed to thermokarst, and we're thinking about general classes of thermokarst processes, including mineral low-lying terrain that tends to be associated with thaw lake formation, low-lying organic soil-rich landscapes that tend to be dominated by wetland or peatland type processes, and then more terrain-rich mineral hill slope type terrain that tends to be associated with erosional and hill slope processes. Now, we were really designing this spatial framework at a circumpolar scale, so we drove our spatial modeling with global products. I've listed a number of them on the slide here. This work was led by David Olefelt, who was a postdoc in my lab at the time. He has now fledged, gone on to his own position at the University of Alberta. This is just some of the mapped products that are resulting from the framework that we created. I'm showing, again, just spatial distributions at the large scale for these different classes of thermokarst trajectories. What we learned through this activity is that thermokarst in total affects just about 20% of the northern permafrost domain. But these are regions that tend to store a disproportionate amount of soil carbon, again, because they tend to be affiliated with poorly drained, mostly ice-rich soils. We've tried to engage in a number of validation type activities to increase our confidence in these maps. We have taken a number of approaches. I just want to talk about one of them today, and that is that we created a living database of all of the coordinates of field site locations that we could find in the literature where thermokarst was known to occur. And I'm just showing you some of the co-locations of this field site network mapped on top of our predicted thermokarst predisposition for Alaska and parts of Western Canada. In general, when we do this kind of co-occurrence, there's fairly good agreement between known thermokarst field sites and what our mapping activity tends to predict. So once we had a better sense of some of the spatial patterns of thermokarst disposition patterns, the next step that we took was to try to get a better understanding of how those patterns of thermokarst might alter ecosystem carbon behavior. We're really interested in an ecosystem approach here. We would like to understand changes in the permafrost carbon pool, carbon in the active layer, as well as vegetation carbon pools. Again, we're thinking about generalized thermokarst classes here because we're running this at a very large scale. I'm going to talk about 3 trajectories of thermokarst: lowland organic terrain, again dealing with peatland and wetland processes, lowland mineral terrain that tends to be affiliated with thaw lakes, and then upland mineral erosional type processes. For each of these 3 trajectory classes, we developed conceptual models of change, and I just want to show you our model of change for the lowland organic class, these peatland classes. So we know that thermokarst and thaw in frozen peatlands tends to lead to the development of these collapse scar bogs or fens, or under very ice-rich conditions can also lead to thaw lake formation. But these young ecosystem classes, soon after thaw, undergo further change over time through succession. So we were trying to model that entire trajectory of ecosystem succession. We used our spatial predisposition maps to get a better understanding of the area of land affiliated with each of these boxes within this ecosystem successional model. And then we went into the literature and used data synthesis to summarize 2 different types of data. One is the transition rates as one ecosystem state transitions to the other, so the timing of each arrow in this model. And we also use data synthesis to calculate mean carbon fluxes, changes in soil carbon pools and vegetation carbon pools. And we also tracked fluxes of carbon dioxide and methane, again using data synthesis. So with this kind of model framework, I can show you output like this. I'm showing cumulative carbon balance and petagrams of carbon per year over time for various ecosystem states within this conceptual model. So the blue line shows that in frozen state, these permafrost peatlands are actually taking up carbon from the atmosphere. They're small net sinks. They're accumulating peat. But there's a considerable amount of data from chronosequence studies in Western Canada as well as Alaska that shows Thermokarst in these frozen peatlands tends to convert those net carbon sinks to substantial carbon sources to the atmosphere. And that carbon source is driven by a loss of carbon from the permafrost pool, so carbon at depth. Now, these large carbon losses from previously frozen peat are partially offset by new peat accumulation and new vegetation growth in older collapsed scar bogs. So some of that large carbon loss is actually offset by new carbon uptake. Again, we can think about this in terms of our successional dynamics. So we're interested not only in understanding carbon behavior as ecosystems transition through succession, but we're interested in the entire trajectory as a whole, and what are the implications of thermokarst in general. We repeated this kind of conceptual modeling for the other two types of thermokarst trajectories, for the lowland mineral and the upland mineral terrains. So now I want to just show you some of the numbers that we derive from this approach across all of these three types. As part of a larger sensitivity analysis, I created 3 scenarios of emissions. Our median values were used to create the central emissions scenario. I used very conservative values. These are all based on empirical estimates, but I used all of the combinations that tended to lead to lower emissions to the atmosphere as part of the best case scenario. You can consider that a conservative estimate. And on the flip side, all of the values that tended to lead to larger emissions were used in the worst case scenario. But all of the values are plausible. They're all based on empirical values. You can see that in the best case scenario, some of the thermokarst trajectories are also actually associated with net uptake of carbon, so no net loss of carbon. But that's not true for the central or the worst case emission scenarios, the worst case scenarios involving very substantial losses of carbon to the atmosphere. So our original intent was to compare these estimates of thermokarst-related carbon loss to modeled estimates that are focusing on top-down thaw. So I'm trying to do that here. I've just taken some ranges in modeled estimates. Again, models that focus on top-down thaw on the left. The scenarios in the middle actually include some carbon losses through thermokarst, primarily focusing on thaw lake carbon transformation. So how do our data compare? The red bars are from our central estimates, and I'm showing you some ranges in our model scenario from the best case to the worst case scenario on either end. What we learned from this effort is that potential carbon releases from thermokarst have the potential to be as large as those estimates of carbon release coming from top-down thaw. And this is despite the fact that thermokarst is only affecting about 20% of the landscape, so it's a hotspot type process. So I think now that we know that the potential for carbon release from these lateral processes are large, we really need other approaches. We need process-based models to look at this issue in more detail. I want to switch gears now a little bit and talk about some more general issues, some of the opportunities and some of the challenges, perhaps, that come from a conference like this. In this room and at this conference, there are such a diversity of backgrounds and a diversity of experiences. And again, there are many, many opportunities that come from that. The challenges come from the wide range that we have in different scientific cultures, different languages perhaps that we use. We can all place ourselves in our own research programs along this continuum, say perhaps between natural sciences and engineering or social sciences. Likewise, we all sit somewhere in our own personal space along a continuum from basic discovery to innovation or applied science. And there can be challenges crossing these various gradients. So how do we bridge this conceptual divide? Some of you may have found yourself sitting in a room over the past couple of days listening to a carbon talk, perhaps, like scratching your head saying, What is this carbon stuff? Okay. What I want to argue is that Thermokarst is one of the emerging issues that is so transformative that I think it has the power to unite many disciplines together. Thermokarst involves such dramatic land cover change. It affects issues related to fine scale or regional scale infrastructure and engineering projects. Land cover change associated with wildlife impacts and migration corridors. Resource extraction, sometimes that can have national level security risks or implications, economic implications, traditional land use that can cut across many generations. All of these issues really need to reduce uncertainties about Thermokarst. I want to talk very quickly about some of the thought processes that we've been going through, trying to think about how we can use some of the tools that we have been using within the permafrost carbon network to address very different questions. I've had the great pleasure of working with folks in the Northwest Territories or with research experience in the Northwest Territories, such as Steve Coquel, Steve Wolf, and Sharon Smith, thinking about how we might apply our Thermokarst vulnerability mapping to various issues in the Northwest Territories. For example, the government of the NWT is investing many millions of dollars in a fiber optics cable that cuts right across the entire Tioga region of the NWT. It's going to run all the way up to Inuvik in the tundra. The green portions on this map on the left show sections of that fiber optic cable that have already been constructed. This project is designed to bring high-speed internet to the north. But very soon after burying some of this cable, environmental assessments have shown some widespread evidence of gully formation and erosion, presumably related to Thermokarst. And we're really interested in using this almost as a test bed for sort of matching our predictions with Thermokarst vulnerability maps. How well are our maps doing in areas where there is known subsidence because of this human activity? This region is of interest for many, many reasons. There's a strong history of permafrost research here. It's also an interesting area for resource extraction. It's home of the Knoll Shale Formation, arguably the largest source of shale oil in North America. This is largely an untapped resource, but there are many companies standing by, waiting for a better economic climate before they start to pursue extraction. There's a lot of talk about fracking to pursue extraction in this region, and I would argue we have very little information on how fracking might influence permafrost or Thermokarst in this region. So again, we're interested in how we might be able to use some of our tools to improve understanding of this area. And of course, permafrost is not just responding to climate or human land use, it's also responding to natural disturbance, changing fire regimes in the north. 2014 saw some of the largest fire activity in the Northwest Territories, and we have been tracking the effects of some of this fire activity on ecosystem behavior, both in the short term, but in the long term through permafrost dynamics. And this is through collaborations with Jean and Tony, and they are here today. So I just want to conclude, many of us are here because we love the North. We all work in the North or on Northern issues. Many of you live in the North. We are a permafrost community. We may ask very different questions, but we rely on very similar types of data. Engineers and ecologists, we need ground ice data. We need geomorphology data. We rely on similar types of information. So I think we need to try to come together to join forces and collect, put our efforts behind collecting those data that the community defines as being of mutual interest. And if we can do that, I think we can truly form a permafrost nation. Thanks very much.